Okay, so we will start today by looking at vertical motion under the action of gravity. So when we are looking at the equations for this type of motion, there are two important considerations that we will take, okay, or two assumptions you can understand as. So one assumption is that yes, so what we are going to discuss today, Ishan, is going to be part of what is coming in MT3. Okay, I will tell you a list of questions to do from HC Verma and the module also accordingly, so you will be prepared. So the first assumption is that we're talking about motion at distances, or you can say height, okay, whether you call it distance or height, it's one and the same thing, from the surface of the earth. Okay, that from distances, motion at distances that are negligible compared to the earth's radius. The radius of the earth is approximately 6,400 kilometers. So we are talking about, vertical motion where the maximum height or the maximum distance from the earth's surface may be pretty large, like few kilometers or even hundreds of kilometers, but it should not be of the order of thousands of kilometers, because it should be negligible compared to the earth's radius. Okay, so that the acceleration due to gravity is uniform. You can treat the acceleration due to gravity as a constant quantity or as a uniform quantity. That is the first assumption. And the second, so that acceleration due to gravity typically value is like this, or sometimes it approximately take it as 10 meters per second square in all numerical problems. Okay. The second assumption is that on an object in this type of motion, any type of air drag force, air drag or wind resistance type of force is absent. Is absent or again negligible. Therefore, the net force is its weight, and therefore the acceleration equals to acceleration due to gravity. So these are the two assumptions that we will think of as, blanket conditions for all type of problems that we are doing under this section of motion under vertical motion under gravity, as well as the next section which we'll be doing, which will be projectile motion in the next lecture after today. So that one also will be, any type of motion under gravity that we are studying at this stage, we will make these two assumptions, that we are talking about distances which are small enough compared to the radius of the earth that there is no significant variation in the value of small g, that is acceleration due to gravity. It's a uniform quantity. And secondly, that on the moving object, apart from weight, there is no other force acting like air resistance or air drag or wind resistance or any type of force. So for example, if you observe something like a brick under free fall or a heavy rock under free fall, it will be more or less like this situation that we're talking about over here, because the weight of that object will be very large compared to any type of air drag or wind resistance force acting on it, unless there's an extremely high amount of wind, which we're not getting into. Okay, but you take something like a, like a cotton wool ball, okay, or something made out of light feathers, and you will see that its weight is so less in comparison to its the amount of wind resistance or air drag acting on it because of its large surface area and its extremely low density. So such an object will not move in the same way like we're discussing here, because there will be a number of other forces other than gravity, like air drag and wind resistance, which will become significant. Okay. So again, in this section, we are not going to be discussing that type of situation where there are other forces which are significant. For us, the only significant force is going to be the gravitational force. That is why under these assumptions, such a motion, vertical motion under gravity, becomes a special case of what we have discussed in the last lecture, that is uniformly accelerated 1D motion. So hence, in such conditions, vertical motion is a uniformly accelerated 1D motion. When we start applying the equations, you'll see it's nothing new for us. It's the same thing that we have learned in the last lecture, but with a special case that the magnitude of the acceleration of such a body during that vertical motion is 9.8 or approximately 10 meters per second square, and downwards it's uniform. So you can just make a sort of brief note of the assumptions if you like, or you can just make sure you understand them. Okay. If there's any doubt related to this, please let me know. Okay, let's begin then. So the first case we will see is free fall. Okay, that is, you just drop an object and it's falling freely under the action of gravity. So free fall of an object, or in this case, we can treat it as a particle, dropped from a certain height. So dropped means it's not been given any initial velocity. So this is like one of the simplest cases that you can think about, that not only the acceleration is uniform, but the initial velocity is zero. So it's, excuse me, it's like a very straightforward situation. So let's say this is some kind of horizontal floor level, and from some kind of heighted position, the particle is dropped. That means its initial velocity is zero at time t equal to 0. So let's also assume that it's at a position which is at a distance of h from the ground, and the value of acceleration due to gravity is g. So for this situation, what we'll do is, as the object is falling, t equal to 0, whatever its position is, we will take that as our origin of the coordinate system, and the direction of its motion, that we'll take as our y-axis. We'll take this as our y equal to 0. Then what will happen is that, suppose by the time it's t seconds, the object has reached here, its velocity has become v. Then for writing our equations of motion, we can say that its initial velocity is 0 and its acceleration is plus g, because g is in the downward direction and we've taken the y-axis downward. That is our reference frame. In a one-dimensional motion, the reference frame is a single axis. Okay. So from this information, we can see that if it's made a displacement of s during this time, this was at t equal to 0. Now at time t, its velocity will become gt and its displacement will become half gt square. So its velocity is varying with respect to time while it is in free fall, according to this kind of a relation. And its displacement in the downward direction is increasing with respect to time in this kind of a relation. Parabolic or quadratic graph, half gt square. So now the other thing we can see that suppose this finally hits the ground at t equal to capital T with the final speed or an impact speed I. So you can also see that if the particle hits the floor below at a time t equal to capital T, this is the total time of the free fall with an impact speed v equal to vi. Okay. Then from these two equations, we can calculate both of these things. In fact, we can also write the third equation that p square is equal to 2gs. So we can make use of this one also. Okay, so from equation 2, you can see that at t equal to capital T, the displacement should be equal to h. So h should be equal to half gt square. So the time taken to hit the ground below, provided the ground is at a distance of h. Now, why I've taken the displacement as positive of h? Because the downward direction is positive. So when it hits the ground, the displacement of the object from t equal to 0 to that time, this whole vector from the initial point to this lower point is h in magnitude and downward in direction. So it's positive of h. So the time becomes, cross multiplying this and solving this for time, it becomes square root of 2h by g. This is one important formula. And from equation 3, you can see that at t equal to capital T, when the displacement is equal to h, the velocity is the impact velocity to the ground. So use the third equation, v square is equal to u square, that is 0, plus 2as, so that is 2gh. So from this we get the formula for the impact speed, root 2gh. So apart from the two fundamental equations that are giving you displacement and velocity as a function of time, we have two more important formulas specifically, which tells you that if you drop the object from a height h above and it goes and hits the floor below, then it will hit the floor after so much time, capital T, and it will hit the floor with a with a downward velocity or an impact velocity of root 2gh. Okay. So just make a quick note of this. This is, as I said, the simplest situation of straight line motion with uniform acceleration, because not only the acceleration is uniform, but the initial velocity is zero. There can't be anything simpler than this in this particular situation, uniformly accelerated motion. We'll look at a couple of numerical problems based on this, but first write this down. Yeah, Rishabh, I'll scroll down, but the thing is, like, after this, there's just one more thing written, that vi square is
Okay, sir.
48, so square root of that, so that formula. So at your board or school level exams, you can get, you know, school or junior college level exams, you can get very direct questions where you have to just substitute this formula. So for example, a particle is dropped from a height, say 20 meters, and take g as 10 meters per second square. So find the time taken to hit the ground and the impact speed. So they're just directly formula based, so nothing to do here. Just except that you must make sure that you substitute everything in SI units so that you get the answer in the proper unit. And but obviously this is not the type of question that you'll be practicing at the JEE level, because it's direct formula based. So the questions at JEE level will be a little bit more indirect. So let me demonstrate with a couple of examples. So this is not for your JEE level question. This is for your board level question. Now let's look at a JEE level example. So we want to find the ratio of the displacements in the 4th second of motion to 5th second of motion for an object in free fall. Again, we'll take g as 10 meters per second square. Okay. Now, even this question is not difficult, but just that it's indirect compared to the above question. There's no direct formula in which you can substitute, but you have to make use of the standard equations. So remember, free fall under gravity is a special case of uniformly accelerated 1D motion, and that too with u equal to 0. So you know how to modify the three equations with u equal to 0 and acceleration equal to g. And then just according to the language of the question, you have to decide which of the equations to use or which combination of equations to use to come to the answer. So just try this out. I'm expecting you people to send me the answers of this pretty soon.
Sir, is the initial velocity in this question to 0? It's not true for.
Okay, so the answer should be, people, the answer should be 7:9. Okay, so let's see how this is working out. Yes, Siddharth, very good. My three, lot of you have got this. Okay, good. So let's see. So like one is, we can just solve it by a very fundamental method. We can understand that if the object started from rest at t equal to 0, u is equal to 0, and let's say it's somewhere here at t equal to 1 second, then further down at t equal to 2 seconds, further down at t equal to 3 seconds, and further down at t equal to 4 seconds, and finally somewhere here at t equal to 5 seconds. So in our diagram, we'll understand that this is the displacement from here to here. This is the displacement in the 4th second. That is from t equal to 3 to 4 seconds from the start. Okay. And similarly, this one over here will be the displacement during the 5th second. So that is. Now, of course, we can calculate all these things. This is the displacement after 3 seconds. This is the displacement after 4 seconds. And this is the displacement after completion of the 5th second. So you can see that S4 is total displacement after 4 seconds minus total displacement after 3 seconds. Now displacement is half gt square. So So next step, this is going to work out to something quite simple. So this is half g into 16 minus 9. This is half g into 25 minus 16. So it's or if you remember last time we had written a general formula also for displacement in the nth second. That is the difference of displacements in n seconds minus n minus 1 seconds. That was u plus half g into 2n minus 1. So in this particular case, sorry, half a, this particular case u is 0, but a is equal to g. Okay, so this was the formula. So in this particular case, put u equal to 0, g equal to, a equal to g. So displacement in the nth second in general is g into 2n minus 1. So displacement in the third second, sorry, in the fourth second is by 2, and displacement in the fifth second is. So if you remember this as a special formula, that's also fine. But as I said, you don't need to memorize it as a formula. You can just understand the logic of how it was derived and apply that logic in any question where you need to calculate this kind of thing. Anyhow, hope this question is clear. Please let me know in case of any doubts. Number of people have sent me the correct answer, so that's good. Okay, let's move on now to another example. And again, there is some kind of indirect question which is asked. So Ishan, I've mentioned this, acceleration is uniform, so velocity is increasing. Velocity is not constant, beta. Acceleration is uniform. G is the constant acceleration. So velocity is increasing. Case of uniformly accelerated motion along a straight line. I discussed that already. Written that down above also. So okay, so now a body in free fall from a height h, okay, makes a displacement of 90 meters. Sorry, makes a displacement of 100 meters in the last 2 seconds of its motion just before hits the ground. So take g equal to 10 meters per second square and find the total time of free fall and the height h from which it is falling. So again, pretty simple type of question. Just try this out. Yes, Parv, very good. That's correct. Shivansh, correct. Very good. Okay, let's look at the solution. You should be getting the total time as 6 seconds, and therefore you should be getting the total height as 180 meters. So let's see how this works out. So again, t equal to 0, the object starts from free fall. Now suppose it hits the ground below at a time t. So where is it going to be at 2 seconds before that? It's going to be somewhere here at t equal to capital T minus 2, having some kind of a velocity v like this. Okay. So this is the displacement that is happening in the last 2 seconds. That is the displacement from t minus 2 to t seconds. So that is given to us as 100 meters. Okay. So displacement from t minus 2 to t seconds is the total displacement after t seconds minus the total displacement after t minus 2 seconds. Okay. So that is equal to half gt square minus half g into t minus 2 whole square, and that is given to us as 100 meters in magnitude. So 5 into t square minus t minus 2 whole square is equal to 100. So when you open this bracket, t square cancels out, okay, and you get 4t minus 4 is equal to 20. So t becomes 6 seconds and h becomes 180 meters. And if required, you can find the impact speed also. Also, we know that it will hit the ground with a speed of 60 meters per second. Okay. Okay, so these are some examples of applications of that first case, free fall under gravity when an object is dropped from a certain height. Now the second case we'll see is when an object is still in free fall, but it is not dropped, it has been thrown down. Okay, so an object or particle or whatever thrown down. Okay. Or in proper language, you will say it is projected vertically downwards from a certain height. Projection means throwing something. Okay, so projected vertically downwards from a certain height above the ground. So let's look at this case next. So imagine the same scenario. A person is at a position where he is holding an object at a certain height above the ground level. So this height is h. But at what happens is that at t equal to 0, he or she throws it downwards with an initial velocity u. So again, what we'll do is we'll take our axis, y-axis or x-axis or whatever downwards, and the origin at the point of projection. So this time we will write our initial velocity as plus c, and because the acceleration is also in the downward direction, so the acceleration will also be plus g. So after some time, if the object has reached here, let's say its velocity being v and its displacement from here to here being s, so we can say that this time v will be u plus gt and s will be equal to ut plus half gt square, and v square will be equal to u square plus 2gs. So these will be the corresponding three equations, and we won't write direct formula. Instead, for numerical problems, we'll solve using this. Okay. So let's look at a direct example first. Okay. So a ball is thrown down at a speed of, let's say, 10 meters per second from a height of, let us say, 500 meters, pretty large height above ground. Find the time taken to hit the floor and the impact speed. Take g as 10 meters per second square again. Okay. Just make a small modification to this value. Just a minute. Okay. Make the calculation easier. We'll take 450 meters. So even though the height is in that sense quite large, it's half a kilometer almost, but it's nothing compared to the radius of the earth. So there's no problem with the assumption that g will be uniform. No, Ishan, you can't use that, no? Because, and first of all, v is square root of 2gh, and that is when u is 0 beta. Here the equation is written above, now the third equation, see what it is, v square is equal to u square plus 2gs. So you have to use that if anything, okay? But to use that equation, got it now? So v is unknown, u is known, and the displacement will be equal to h at the moment when it hits the ground. So from that you can find the final velocity. That's one method. Yes. Okay, so few of you have sent me the answers. The answers don't appear to be correct. Let me check. So if we go with this thing that at t equal to t, which we don't know, the displacement is equal to the total height, which is 450 meters, and the velocity is something that we don't know. So v square is equal to u square plus 2gs. U is of course something that we do know. U is this. So v square is equal to 10 square plus 2 into 10 into 450. It's 100 plus 9,000. And we are getting the velocity, okay? Yeah, so root 91 can calculate will be 9 point something. See, 91 we can write as 81 plus 10.
9.5 something.
Yeah. Okay. So approximately
To 9 by 16 to 0.56.
wait a minute, I've got this value wrong, I think. Okay. We just check. Yeah. Okay. So this is a little bit more accurate. So this is your velocity and v equal to u plus 80. So this 95.6 is equal to 10 plus this a is g. 10 into capital T. So the total time you will see will come out to be about approximately 8.56 seconds.
Sir, can you explain the calculation of root
Yeah,
91?
I'll explain. That is, I use something called binomial approximation. I'll explain that also. Actually, the correct value of this square root 91 is closer to 9.54 than 9.56, but this approximation method will give us this, which is okay enough for basic approximation. Okay. So this method that I've used here, it is something called binomial approximation, which you will study in mathematics later, that 1 plus x to the power n can be approximately written as 1 plus nx if x is very small compared to 1. So what we do now is, for example, I want to calculate square root of 91. So that is 91 to the power half. So obviously there's no point in writing it as 1 plus 90 because 90 is a very large number. But the closest whole square I can see is 81. Okay. Or 100 for that matter. I can also write it as, that will probably give me a more accurate answer. But let me show this method first. Okay. So now what I do is I take 81 common from this. Okay, so it is 81 into 1 plus 10 by 81, whole thing to the power half. So that is 9 into 1 plus, now 10 by 81 is almost 1 by 8. It's slightly smaller, but so 1 by 8 is small compared to 1. So I can use this approximation. I can use this thing because, okay, so this will become 9 into 1 plus, now n is half and x is 1 by 8. That's how I got this. Like this is so that is 9 plus 9 by 16, which is approximately coming out to be 9.56. Okay, this is okay for approximation. That's okay now. I could also write this as
100.
yeah, even this would work. Something like this. Okay, so
Only half into 0.0.
okay. So 0.045 into 10 हो जाएगा. So that will be, you can see it's coming in that kind of range only. Same 9.55, 9.56, something like that. So this is called the binomial approximation method. Don't worry, you will learn it later in maths also. Okay, so okay, anyhow, now let's move on to the next situation. in vertical motion under gravity, and that is the third case where we project something vertically from the ground, vertically upward projected. Will be so this is slightly more complex situation, because this is that situation where the object, when you project it from the ground level vertically upwards, it initially decelerates because gravity is acting downwards and the initial velocity was upwards. So as it is going down, it's going up, it's kind of losing speed. So at some time t, if it has a speed v upwards, this v will be less than u. Okay, but also what will happen is as it continues up, at some stage, because it's decelerating, it will come to an abrupt halt, rest for at some instant, and then after that it will start coming down. So only for demonstration I'm showing it as a parallel line, but actually it will exactly overlap the line that it went up along, retrace that same path, and then finally it will come back and hit the ground exactly at the same spot. So again, at because of demonstration purpose I'm showing this like this, but actually the downward path exactly overlaps the upward path. Okay, so at t equal to 0, now what we'll do here is, because the motion is happening in the upward direction, we will take this time the vertically upwards direction as our y-axis, because the initial velocity is vertically upwards. No, so here beta we are talking about vertical. Okay, Akshat, that is projectile motion. We will come to that when the angle is variable. So then it's a two-dimensional motion. Then the path is not straight line. Okay, we'll see it's a parabolic path. So that is the second chapter of this thing. Okay, motion under gravity, which is projectile motion. We'll come to that. But here we're talking about strictly vertically projected. Okay, so it's opposite to gravity. Vertical projection means opposite to small g. It's projected. So throughout this motion, g is acting like this. So we'll take a y-axis upwards and our origin at the point of projection. So at t equal to 0, the initial velocity will write with a plus sign, but the acceleration will write with a minus sign. So at some time t, the velocity will be u minus gt. That is the velocity at this point of time. And the displacement will be ut minus half gt square. And the third equation will become v square is equal to u square minus 2gs. So these are the three equations that we use. Okay. Now, when it reaches this point where the velocity is 0 for a moment, we will write its displacement as h, where we'll understand h is the maximum height. So we will be able to calculate these things, maximum height, the total time of the vertical motion, etc., using these equations. So therefore, you can see, first of all, at the instant when s is equal to h, that is, it is at the highest point. Momentarily, its velocity is 0. So from equation 3, we can see that 0 is equal to u square minus 2gh. So we get this formula that the maximum height it reaches depends on the initial velocity in this manner. So this is the first important formula. Make a note of this, then we'll come to the time capital T. Okay, now the other aspect of this you can see is that at t equal to capital T, the total time of basically what we can say is ascent plus descent. Okay, so at t equal to capital T, the displacement becomes 0 because it's back to the point of origin of the motion. Where the motion starts from, the particle has come back to that position. Okay, so from equation 2, we can see that 0 is equal to ut minus half gt square, or factorize this, this will give you two roots, but one of them you'll reject because that is t equal to 0. That is the initial time. So that will give you the time of flight. So the first root is t equal to 0, which will reject. The second root is t equal to 2u by g. So in the language of vertical motion, sometimes you also call this the total time of flight. It's not like the object is flying. I mean, it's not a organic or living being that is flying in that sense. Okay. Nor is it having any form of propulsion. It's simply moving under the action of gravity. But so this is also called total time of flight. But basically what it means is the total time to taken to go up and then come back. And I mean the total journey, that is the ascent plus the descent till it's back to the starting point. So these are two standard formulae, whereas for anything related to a quantity we are calculating other than h and t, that is the maximum height and the total time of flight, if we are calculating anything else related to the motion, then we make use of the three equations that we have written above. Remember the sign convention while writing those equations, our axis is upwards. So any quantity which is having a direction in the upward direction, it will come with positive sign. Any quantity having a direction downwards, it will come with a negative sign. Okay, so hope this is clear so far. Now the next thing to understand about the motion is that at the highest point, it is S equal to H, V is equal to 0. Therefore, from equation 1, 0 is equal to U minus GT. So the time at which it reaches the maximum height is U by G. Okay, and you can notice that this time is equal to capital T by 2, because capital T was 2U by G. Okay. So this tells us something important, that 0 to T by 2 is ascent, and then T by 2 to T is descent. Okay. So half the duration of motion is for ascent and descent respectively. It exactly divides it into symmetrical halves. And the other thing is, at T equal to capital T, when it impacts the ground, V impact will become U minus GT from the first equation. So that will become U minus G into 2U by G. So you see it will become minus U. So the impact speed is equal and opposite to the projection speed initially. So it impacts the ground at T equal to capital T with equal and opposite, with a velocity opposite in direction and equal in magnitude to the initial velocity. Okay, so whatever speed with which you threw it up, it should return back to the ground at that same speed, but obviously the direction opposite. And during that motion, going up and down, the upward journey and the downward journey, the ascent and descent, are perfectly symmetrical. They are like mirror images of each other. Half the total time it takes in going up and the remaining half in coming down. So these are some important aspects to remember about this case, the vertical motion under gravity when something is vertically projected from the ground. Okay, so this whole thing also works out in a type of symmetry, which we'll understand through the graphs. Symmetry in the ascent and the descent part of the motion. So if you visualize the velocity time graph here, based on what we just saw in the previous section also, about the values and all, it starts off with the initial velocity of positive u. At the highest point, it's at rest, and that is the like the midway of the total journey. So if this is the total time of the motion for ascent plus descent together, then this is exactly halfway point when the velocity becomes zero. And by the time it descends and reaches the ground, its velocity has become minus of v. So you can also see that in this graph, there's another type of symmetry, that if there is some time t1 when the velocity is v1 on the positive side, there will be some symmetrical time t2, such that if this time t2 is equal to capital T minus t1, like if this is 2 seconds after the start, then this time t2 is 2 seconds before it hits the ground. So in that case, the velocity here will become minus of v1. If t2 is equal to capital T minus t1, then the velocity at this stage will be negative of the velocity which is at this stage. So that is the symmetry. And similarly, if you look at the displacement time graph also, you will realize the same symmetry in practice. So displacement time graph is like that situation where u is positive and a is negative that we discussed in the last lecture. So it's a parabola which is downward opening. And since we consider only that part of the displacement, I mean that part of time till it hits the ground, after that we're not considering any type of motion happening. Neither it's digging into the ground, nor we assuming it's bouncing or anything like that. So for us, the motion abruptly stops at the instant when the displacement becomes zero. So that is the total time. Whereas we can see that it reaches the maximum height at the time of t by 2. So capital T is 2u by g, and this maximum height is therefore u square by 2g. And this also you'll see that symmetry thing that I was telling you about, that if there is some time t1 at which the displacement is s1, then on its way down also it will be at that same displacement, but at a time t2 where there is this symmetry that t2 is equal to capital T minus t1. That is, this interval of time here has to be equal to this interval of time here. Only then this displacement is common, or the velocities are equal and opposite. So this is the symmetry of the upward and downward journey represented graphically. So make a note of this, and we'll see some typical type of question based on this idea. Okay. So next example, a particle is projected vertically upwards from the ground at t equal to 0 with velocity say u. G is equal to 10 meters per second square. It reaches its highest point, or you can say maximum displacement, at t equal to 5 seconds. So from this we have to find u, the maximum height itself, the total time of flight, the standard things. You have to find the displacement at t equal to 4 seconds, t equal to 5 seconds, and so not s but t, and again at 6 seconds. And the next part, which is really interesting part, we have to calculate the distance traveled is actually actual path length from t equal to 0 to 4 seconds. How much distance is traveling in 4 seconds? Whereas B part from 0 to 6 seconds. That is from the starting till 6 seconds. How much is the total distance traveled? Not the displacement, but the distance. Note in the second question, S is displacement. Okay. In this question, S is not distance, it is displacement. Okay, so again, you will see that the solving of it is pretty formula based ultimately, but just for the understanding of especially how to work out the third part, if you understand this symmetry of the ascent and descent, it's a little bit easier to figure out, okay, how to apply the equations. Okay, the first part is quite straightforward actually. Just if you think of the standard formula that we developed above, okay, should be pretty easy to figure that out. Work it out quickly and send me the answers. Okay, very good, Parv and Anand. Uh, you got this much correct. Okay. Capital T, Parv, is the total time na, of the journey. Total time of flight, what we call the ascent plus descent. Yes, Akshat, that's correct. Very good. Parv, correct for the total time also. So now you people have to just think about the last part of the question, how you will calculate the distance in 0 to 6 seconds. The rest of the things you'll get from just application of what you've got for the first part. Yes, very good, Adinath, that's correct. Parv, this is the answer for the last part. Yes, very good. Siddharth, very good, correct. Third part is also correct. Okay, very good, Adinath, that's correct. So most of you have got the answers correct now. So I'll just put up the answers here. This is 50 meters per second. Maximum height will come out to be 125 meters. And the total time will come out to be 10 seconds. So this first part you can see from the fact that at t equal to 5 seconds, it's at the highest point. So the velocity is 0 and the time is half the total time of flight. Okay, so which is u by g. So from this information, we know that u is 5 seconds multiplied by g, 50 meters per second. From that, we know that maximum height becomes 125 meters and total time becomes 10 seconds, 2u by g. Okay, so these three things come directly. Now for this second part, s, at t equal to 4 seconds, just substitute in this. So you'll see that with the displacement as 120 meters. Okay. In B part, you know that displacement will just be maximum height, which you already calculated above. But interestingly, at t equal to 6 seconds, you can see that displacement will again be 120 meters, even without calculation, because if you take t1 as 4 seconds, you can see that this kind of t2 is 6 seconds. Okay. So therefore, displacement at 4 seconds will be equal to the displacement at 6 seconds, whereas velocity at 6 seconds will be negative of velocity at 4. So just using the symmetry, you can just cleverly work it out like this, or you can always substitute in the equation also. So if you're substituting in the equation, you'll get as 50 into 6 ut minus half gt square. 300 minus 36 into 5, 180. But this calculation is not required because you can understand that there's a symmetry between this time and this time, because this is the half time. Okay, or the total time was 10 seconds. Now, when it comes to the last part of the question, the distance traveled, you just have to be a little careful that you are looking at an interval. You might be looking at an interval of time where the direction of motion is changing in between. So distance will not be the same thing as displacement. So that will happen in the second part when you are taking the distance traveled from 0 to 6 seconds. Because now that you understood the rest of the problem, you have understood that the direction is changing or it's reaching the highest point at 5 seconds. So it's going in one direction up to 5 seconds and then it's coming down in the opposite direction from 5 seconds onwards. So the distance traveled will be different compared to the displacement for any time after 5 seconds. So you have to actually calculate how much it went up and then how much it came down. So it went up from 0 to 5. So then it came down for how much time? For 1 more second from 5 to 6. So to calculate how much it came down in that 1 second after reaching the highest point and add that to the maximum height. So that will give you the distance traveled from 0 to 6 seconds. So most of you sent me the answer, got this correct. This will be 130 meters. Okay. Because what's happening is that in the first 4 seconds, it's going 120 meters upwards. Then 4 to 5 is going another 2 meters upwards, because at 5 it's reaching the maximum height of 125. But then at 6 it's coming back to 120. So how much it's come down from the highest point? at t equal to 6 seconds, it's come down by 5 meters. Okay, so that's how you get the total distance to be 130 meters in the first 6 seconds. So in that sense, this was the only part of the question which was a little bit tricky. The rest is straightforward.
Sir, can you once again explain the third part, 0 to 6 seconds?
Yeah, so I'll come to that part. See, so actually the best way to understand that is that now that we've understood that the initial velocity, because it came out to be 50 meters per second, the total time of flight is 10 seconds. So we understand that 0 to 5, it's ascending, and then 5 to 10 seconds, it's descending. Okay, this is the time of ascent. This is the time of descent. Okay. Or you best understand that from the graph. You just visualize the graph of displacement versus time. So because this time is 5 seconds, this is half the total time of 5 seconds. That's why, first of all, in the second part, what we got is that at 4 and 6 seconds respectively, the displacement was the same, right? It was 120 meters. That also tells you that how much further down it is coming from 5 to 6 seconds, because this all we have already calculated in the second part. So now we can see from this that for distance traveled from 0 to 6 seconds, we have to calculate the distance it traveled upwards from 0 to 5. So distance does not depend on direction, but just to understand, whereas it further traveled a certain distance downwards from 5 to 6 seconds. This one was a downward distance travel. So it will be displacement from 0 to 5 because it's upwards only, but mod of displacement from 5 to 6. So the displacement from 0 to 5 is plus 125 meters, but the displacement from 5 to 6 is minus 5 meters because it's coming down by 5 meters. Understood now how it's becoming 130 meters?
Yes, sir.
So this is the only slightly tricky part in this type of question. When you have this type of motion under gravity, that something is going up and then coming down, and you are asked to calculate distance traveled. So you have to break the motion into two parts, the ascent part and the descent part. Separately calculate the distances traveled and add the two. So this is a displacement versus time graph, not a distance versus time graph, because distance cannot start decreasing. Okay. Only displacement is that kind of quantity, which is shortest path from initial to final positions. Okay, so hope this is clear. Now, just one final type of question, which is again based on all these ideas only, but slight variation of the standard formula. we'll just wind up with that final example. So suppose we are again throwing an object from a heighted position, not from the ground level. But instead of throwing it directly down, like we saw in case 2, from this heighted position, we are actually throwing it up. Okay, so something is being projected upwards at t equal to 0. And then when it's like when it goes up and on its descent, when it's coming down, we don't catch it. So we allow it to go past and then go and hit the ground at some time t and with some impact speed vi. So let's do this as a numerical example. So given that the initial velocity is 20 meters per second upwards, as you can see, at t equal to 0, from a height of h equal to, just a minute, 300 meters. Okay, so it's pretty tall cliff, let's say. So 300 meters above ground from that cliff, he's throwing it upwards. Take g equal to 10 meters per second square. So we have to find the time when it hits the ground below. We have to find the impact speed for hitting the ground. And we have to also find the total distance traveled from when we projected the object till when it hit the ground below. Okay. So just a minor variation of the third case that we discussed, but using the same type of equation. So if not having too much difficulty solving this, just try this out.
So initial height is 300, right?
Sorry,
The initial height of the ball is 300 before throwing.
thrown from a height which is 300 meters from the ground. You can see in the diagram now. H is that height where the ball is only from the ground with respect.
Sir, the
Yeah, we will. So hope you have all solved the question. Yeah, so the total time will come out to be in fact 10 seconds. It will go up for 2 seconds and then the total downward journey will be for 8 seconds. But to understand that, what you again do is you take this as your axis. Okay. Take this as your starting point. Okay. So at t equal to 0, your u is plus 20. Okay, but your acceleration will be taken as minus 10 meters per second square. So as a function of time, the velocity will be 20 minus 10t. The displacement will be 20t minus 5t square, and v square will be 20 square minus 20s 2as, like this. These will be the three equations of motion. Now at the time when it hits the ground, it's very good, 10 seconds is the correct answer. 80 meters per second is the impact speed. So when it hits the ground, you can see at t equal to capital T, what is the displacement? It is minus h, because our axis is upwards. Okay. So from these equations, you can see that minus 300 is equal to 20t minus 5t square. Okay. And the impact speed square is equal to 20 square minus 20 into minus 300. And the impact speed is also 20 minus 10 capital T. So what we can do is either we can solve this as a quadratic equation, solving the second equation. So that's one way to go. From equation 2, you have t square minus 4t, right, minus 300 by 5, so that's 60, is equal to 0. That will be so t is equal to 10 seconds, or t is equal to minus 6 seconds, which is not going to be the correct route. Okay. So we get this, then substitute this in equation 1. So you'll get the impact speed as so minus 80. The minus sign just shows you the direction. So it hits the ground with a speed of 80 meters per second downwards. Okay, so this is the whole thing. Okay. Or alternately, what you can do is you can start with equation 3. So you'll get VI okay. Now VI will have to take as negative because you can see the direction is downwards. So we'll take the negative route. Okay. So once we know this, we will substitute this in equation 1. And from that we'll get the time. So minus 80 is equal to 20 minus 10t. So this will show us that the time is 10 seconds. That's another way of going about this. Okay. Now let's come to the total distance traveled part. So you can see that displacement as a function of time is 20t minus 5t square. And this is from t equal to 0 to t equal to 10 seconds. So if you think of the displacement time graph, see this is this case where the displacement is also becoming negative actually. It's not coming back to the same level and stopping. Just a second. I'll have to reshare this file. Okay, so our displacement versus time is going to be this kind of a graph now. So you can see that this is, to factorize this, so you can see that this is 4 seconds, this is 2 seconds, and then finally at 10 seconds, it's becoming minus 300. Okay. So the total distance will be, the total distance traveled from 0 to 10 seconds will be the distance, it goes from 0 to 2 seconds plus the distance it travels from 2 to 10 seconds. Okay, so this will be h and this will be h plus 300. Now h we can calculate like this by the formula. So you'll see h comes out to be so this is the total distance. So just make a note of this, people. It's last part. Yeah, and we'll conclude the session after this today. So that's it for today's session. Wish you all the best, people. Thanks for attending.
Sir, this part is coming in empty.
Bye, sir. Thank you, sir.
Yes, vertical motion under gravity is going to come in MT3, what we studied today.
Okay, sir. Thank you, sir.
Thank you.
Thank you, sir. Bye.